Hi, my name is Manish Gupta, and in this video, I'm going to talk about native sparse attention, which is basically a method proposed by DeepSeek AI. This paper was accepted as the best paper at ACL 2025. So let's get started. How does native sparse attention work? Well, native sparse attention is sort of applicable for long context modeling. When the number of tokens in your input and output are very high, then essentially transformer-based methods can become a little inefficient because the self-attention mechanism, the multi-head self-attention mechanism, is quadratic in nature. Some of these long context modeling tasks include in-depth reasoning, repository level code generation, multi-turn autonomous agent systems, and so on. Right. So in this particular paper, the folks essentially propose three different sparse attention methods: token compression, blockwise token selection, and sliding window based on local context. Right. So to be able to compress the key value caches that they refer to and therefore come up with more efficient attention, right? So this method is basically not an inference time optimization. This method is a training-based optimization, and therefore they apply this thing at train time, right? Let's look at how these three things work, somewhat on this slide using this picture, and then also in detail on the next slide. Okay. So if you're at a particular position T, so there you have a query QT, and I assume you already know about the transformer self-attention mechanism, where you take QK transpose and then apply softmax and then multiply by the value vector, and that's your self-attention, right? So when you're at a position T, you have QT, and you also have all the previous keys and all the previous values. So typical self-attention essentially has the current query paying attention to all the previous keys and all the previous values. However, in this native sparse attention work, they basically propose three different methods to not have the current query look at all the previous keys and all the previous values, but a subset of them, right? The three methods are also shown here: compression, the second one is selection, and the third one is sliding window based stuff, right? Sliding attention. Okay. So as you can see, the first step in their method is to basically take the keys and values vectors and essentially split them into blocks. So maybe, they have blocks of like 6, or you have blocks of 8 and so on, right? And then you apply these methods typically on various blocks. So for example, the compress method actually takes a block of keys or a block of values and then compresses them down to small number of, to maybe, for every block, you just have one key representation in that senses. Okay. So now important blocks from here are taken and used for selected attention. So for a particular query, you want to select which particular blocks of queries, which particular blocks of keys or values you want to use. Okay. And then in sliding attention, it is basically local context based. So for any particular query, rather than looking at all previous keys and values, you basically just want to look at a limited history of keys and value vectors. Okay. So these are the attention heat maps or the attention score maps in that senses. So, a green basically implies that for a particular QT here, you're going to basically look at a particular, for each of the head, you're going to choose a particular block of previous keys or previous values in that senses. So that's basically that. And, let's look at this in more detail on the next slide. Next slide is not going to be based on illustrations, but more on based on, mathematical formulations. So let's go over this in detail. Okay. So how do these three methods work? The token compression, token selection, and the sliding window methods, right? So before going into that, let's talk about the standard attention just to bring in the notations. So given a particular query at time t, you basically have keys and values, all the keys and values before time t. This is a slice notation in Python, right? So all the keys and value vectors before the current time t. Okay. And you use that to compute the attention, where attention is computed using this, right? You do QK transpose, normalize it with the square root of the dimension of the keys, and then you multiply by value vector, apply softmax, and that's, or rather apply softmax and then multiply by the value vector, right? So that's basically your standard vanilla self-attention, okay? Now, what this paper proposes, the native sparse attention paper, is that you take these previous key, the entire tensor, the previous value, the entire tensor, and you apply some sort of a transformation so as to essentially get a transformed key representation, a transformed value representation. So FK and FV are these transformations that you apply to the current query. and then all the previous keys and all the previous values is to basically obtain a transformed representation of keys and values. And the three transforms are what we are going to talk about: token compression, token selection, and sliding window. Okay. Once you have those transforms, of course, what you could do is to basically just compute the attention based on these transformed representations. Now, rather than doing one transform, they actually do three transforms, and therefore, rather than computing, the output just like that, you basically compute output using these three, strategies. In that senses, so C belongs to C, where capital C is a set of these three things: token compression, token selection, and sliding window. Okay. So that's how your self-attention is computed in the transformed world, right? Now, when you're computing the self-attention, in general, the overall set of keys or values that you use to compute the representation, to compute the attention for a particular query, let's denote that by NT. I mean, because each of those three strategies, token compression, token selection, and sliding window, are going to use certain keys and values. So, if you sum up over all of that, the number of tokens NT that you use across all the three strategies, it has to be much lesser than the total number of previous tokens. And that is how the strategy works, right? So that is why their method, native sparse attention, is basically literally sparse, right? By the way, they call it native because, they work with blocks in the entire sparsity enforcing of this attention. And when you work with blocks, block structure nicely is suitable for GPU architectures and optimized utilization of tensor cores, and therefore they call it native self-attention or native sparse attention. Okay. So let's talk about these three methods in detail now. So what is token compression? In very, very simple words, it basically means that you take your keys and values, they are up to a time history t, small t. And what you do is to divide them into blocks, and then you have one representation for each block. Okay. So basically you have a length of t, sequence of length t, and what you do is to build blocks of basically blocks of size L, right? So L is the length of the blocks, and D is the hop, skip length. In that sense, is that from one block you want to go to the next block, so you don't always do disjoint consideration. So what you do is to basically have some overlap across blocks as well. So therefore, D is not same as L, right? So D is basically the hop, the stride in that senses. Okay, yeah. So basically, overall, you are left with T minus L divided by D blocks. So that is basically what you have. And for each of those blocks, you take the key vectors and you essentially compute an MLP-based function, MLP-based features out of it, or MLP-based representation out of it. There is only one key that you obtain, out of one block. So out of all of these T minus L divided by D blocks, you basically obtain so many key vectors. Okay. You do the same thing for the value vectors. I mean, in this slide, I just show what you do with key vectors, but you do the same thing for the value vectors as well. Okay. Blockwise token attention basically means that you have already, figured out blocks over keys and values here. And these blocks are very suitable for GPU architectures and optimal utilization of tensor cores, as I mentioned, right? So you take those, key representations that you've obtained here for every block, and you multiply by query, and then you apply softmax, and that basically gives you some sort of a saliency score or an importance score of this block for the current query. Okay, so essentially, I mean, you should consider this as less like a saliency score coming from the token compression technique. But if the block boundaries that you consider for token compression and for token selection are just the same, then you can literally use the score for token selection method as well, right? Now, notice that when you're doing this multiplication, it's not like you are consuming, you're doing the entire self-attention based quadratic computation. That's not true, because you're taking every query, but for every query, you are not consuming every previous key. You're actually consuming only the block key vectors. So, if basically the previous keys were like 100 and you already, consider block size of 20, and even if you had disjoint blocks, you would not have more than 5 vectors here, right? So therefore, this is pretty fast in terms of computation. Okay. So you basically obtain these importance scores for every blockwise token. Blockwise tokens, and then what you do is to basically also add it up across all heads, because you will get it per head. Remember, you will have these head specific vectors, head specific query, and head specific key vectors, and therefore what you do is to sum it up over all heads. And then finally, when you have these important scores across all blocks, you essentially choose top k blocks. So you can be, or top n blocks as it says, right? So you basically figure out n blocks, you order them by the saliency scores or the importance scores. And then you basically just choose the top n blocks. You concatenate those top n blocks, and that's basically your transformed key representation for token selection strategy. Now you do the same thing obviously for value vectors as well. Okay. Sliding window or the local context-based method is like the oldest method for sparse attention, and that is what you do. You, rather than basically considering all previous keys, you're going to consider only the W previous keys. So which is what the window basically means here. So you'll basically just take W previous keys from the current time t, and that's your transform key vector. Obviously, you do the same thing for the value vector as well. Okay. So overall, you basically have taken k colon t and v colon t representations of all previous keys and all previous vectors and converted them into three transformed representations. The CMP or the compression representation, SLC or the the sliding SLC or the selected token representation, and VIN or basically sliding window representation. Okay. So that's that. So essentially, rather than using all keys and all values for every query, you basically end up using a limited number of keys and values, right? So now the interesting thing that they also do in this work is to really align this from a hardware perspective also. So, for the other two representations, essentially for the other two methods, like the sliding window method and, the token selection method, they basically just apply the standard kernels as in flash attention 2. However, for the third strategy, they basically design their own kernel, just following the same strategy as flash attention 2. The idea is that when you are creating these blocks, if these blocks also align with the groups in GQA, grouped query attention, then it is best, right? So therefore, what they do is to do the following for each position in the query sequence, for each position like QT, the TT position in the query sequence, they load all the query heads within a GQA group into SRAM. So you see, I mean, there is a SRAM and there is a HBM, part of the GPU memory. So following the flash attention. So if you're not looked at my flash attention videos, please look at them. So following that stuff, what they do is to basically load all the query heads that belong to the same GQ group together because sort of they share the same sparse KV blocks, right? So you've applied the same strategy, same three strategies for those KV blocks. And since they share the same KV blocks, I mean, by definition, GQA means for a bunch of queries, you basically have the same keys values. So therefore, they share the same sparse KV blocks, and therefore it's best to load all the heads within a GQA group together, right? So the experiment with pre-training, so the pre-trainer model, as I mentioned, is the training-based approach. So therefore, you need to train as well. So they pre-train a 27 billion parameter model with GQA, where the group size is 4, and MOE, mixture of experts. So basically, they train a mixture of experts-based 27 billion parameter model, which basically means, not all experts are activated at any point of time. So they actually follow the DeepSeek MOE approach, where there is shared experts and routed experts. They have 2 shared experts and basically 72 routed experts, of which every token is routed to a max of to totally 6 experts, 6 routed experts, right? Which basically means that totally their activated parameters are just 3 billion. Now the pre-trained with like 260 billion token worth of data, and the model has like 30 layers with 64 attention heads, right? So that pre-trained with sequences of 8K in length, which they increase over, which they increase in this mid-training phase to 32K using the standard yarn strategy. Okay. So they do experiments on 800 GPUs with optimized Triton, and the results are basically based on that. So these results are like the most, very powerful results. So as you can see, this is on 64K length sequence processing on various kinds of tasks like general NLP tasks, long bench tasks, and reasoning tasks. So the first picture basically shows that whether you use full attention or NSA methodology that they have proposed, the accuracy does not suffer. So in fact, the scores, if at all, are better, if not equivalent, right? So I mean, they're sort of slightly better in that sense. Okay. Now, but the more important contribution is here, where the speed up is significantly high. So both at decode time, which actually matters, at inference time, right? So basically, it matters at inference time, right? So basically, they have a 11.6 times speed up. But what also matters is train time. So at train time, basically the forward and the backward propagation passes, right? So those passes basically have a 9x and 6x speed ups at 64K sequence lengths. Large sequence lengths obviously give you more speed up, right? So a little drill down on this is basically here. And this speedup is basically comparative to the flash attention 2 method. So flash attention 2 is obviously way more faster compared to standard self attention, but they are actually faster even compared to flash attention. Okay. So here you basically observe in this chart, essentially the sparse attention kernel, which is this orange one. And you also see this green one, which is compression and window attention computation. So essentially saying, totally the entire native sparse attention method is green plus orange. And what you observe is that compared to the blue one, there is a significant speed up. This 64K, obviously, it is 9x speed up, as you see here as well. But even for smaller context lengths like 32K, you still find 6.3x speed up for forward time, and similarly, quite some speed up at backward time comparison as well, backward time computation as well. Okay. So, and as we discussed, decoding speed, well, at 64K, it is like 11.6x, but even at like other context lengths like 32K or even 8K, as small as 8K, you do get like 4x speed up, right? And as I mentioned in short, if you basically look at these general NLP benchmarks, these are the general NLP benchmarks, several benchmarks. And what you observe is that compared to full attention, NSA attention does not really lead to any decrement in accuracy. So the accuracy stays flat or slightly better anyway, right? So in short, we talked about NSA method in this video. It is a method to do efficient long context modeling by specifically pre-training models using the NSA approach. The NSA approach consists of 3 different methods: hierarchical token compression, blockwise. I mean, where hierarchy just means 2 levels in that sense is here, right? Blockwise token selection, and then sliding window to implement local context-based sparse attention, right? And they basically show significant speed ups, something like 9x speed up, something like about 11x speed up at decoding time, and significant speed ups for forward and backward passes of at train time, right? Okay, so that's it for this video. Thank you for watching. Hope you liked the video. Connect with me on my LinkedIn and look at my research on my homepage. Thank you.